All right, the recording has started. Voice are still coming in. And there appears to be a lot of issues regarding your attendance. I wonder why. I think some boys have been in trouble, and that is why we are now under pressure to ensure that your attendance is in correct order. So much of pressure for attendance is unbelievable. Farhan, are you there? Yes, he's there. Farhan?
Yes, sir.
Okay, good morning to all of you. And I would like to know where we were on our last class. Had we started governors?
No,
No,
sir.
we had started governors.
No, sir.
No, then what were we talking about last? In
Sir, last class we were talking about thin cell bearings. We had just finished the first plate of thin cell bearing.
oh, initial bearings. My goodness, you're still way behind. So other sections have started the uh, yes, section A has started governors. Section F is quite a lot in governors. But section D and E, they still have a little bit more on the medium speed engines. Okay, we'll try and finish the medium speed engines today and do the governors at a later date at the next class. Okay. Okay, let's go on to medium speed engines. Governors, medium speed engines. Yeah, you're doing thin shell bearings. Yes, here you are. Was it this page?
Yes, sir, it was the last slide.
Okay. Oh my God, number 18. So we still have got quite a bit to do. So right now, how many boys have come in? 34. So it's almost everybody is here. Okay. Okay, somebody else comes in. Karthik Kesari. He's the one who should be coming in before the others. Anyway, so that makes it 35. 34 still showing. Because what happens is in the middle of the class, if somebody starts coming in, then I have to upset the whole plate and then make it so that everybody is able to see it. All right, let's start with our thin shell bearings. Now, there is a lot of write-up about thin shell bearings, but the basic concept you must be able to absorb before you read the technical fine points. A thin shell bearing is a bearing which can be replaced very easily. I will not go into the details of the older type of bearings that were used in the earlier ships, where the molten metal was cast in and then it had to be machined and then it had to be what was that term? Bedding. Bedding of the bearings was required to be done. Bedding was one of the most difficult tasks engineers used to suffer on the ship. And it used to take almost a whole day for one bearing. So now all those troublesome jobs have been eliminated and we have what are called thin shell bearings. Now, thin shell bearing is like a part. If it wears down, you simply change it. If it gets damaged, you simply change it. It's not so costly as the original cast-in bearings. The cast-in bearings were a headache, and if they were to be damaged, the ship would have been immobilized. It was like that. But now with thin shell bearings, it consists of a strip of plate in the form of a curvature. And that plate is made of steel. It is made of a little high-grade steel where there is some amount of springiness. Springiness is there. All right. And on the inside layer, you have a white metal. White metal is made of either tin, copper, lead, antimony, and a few more elements. But the basic four are tin, copper, lead, antimony. Remember? So with that, you may have a little other rare metals also. But mostly these four metals are there. And here again, they are subdivided into tin and lead-based white metals. Some of the white metals are tin-based, some of them are lead-based. The tin-based white metals are very hard, much harder than the lead-based white metals. And it depends on the designer of the bearing or the engine who will decide what type of bearings are to be used. And there are so many parameters he will take into consideration. 1 minute, let me write a little note for myself because I need to find out a little more information. Other elements. You see, sometimes it is a learning process for me also. When I give you a lecture, there are some points I say, why didn't I find out about that? So that point I have to write down and then I go and find it out. So I was talking about tin-based white metals, lead-based white metal. Lead-based white metal is a little softer because lead, everybody knows, is a little soft. All right. Now, the steel plate, which gives the main backup, has a layer which forms the bonding of the white metal to the steel. That is the basic requirement of a thin shell bearing. The white metal will not adhere to the steel very easily, and it is risky if it is not adhering to the surface because it will come off when the shaft is running in the bearing. So they use generally an inlay. The inlay is used as a sort of a bonding device. Sorry, it is called the lining, not bond inlay. It is the lining, a lining between the white metal and the steel to help it to hold together. There are a lot of questions that have come up that if the temperature of the white metal is coefficient of expansion is more and the steel is different, then they'll come up. Now, this question was raised in the last class by section E, and also I had an explanation that in this bearing, the temperature differences are not so vast. In other words, it is running in the temperature of 40 to 65 degrees centigrade. 40 is the inlet of the Lubboil temperature, and when it comes out, it is about 65. So let us say that bearing goes up to a temperature of 70 degrees centigrade. So the differential temperature between the two is not that high. It is different in the case of exhaust valves, which we will do subsequently to this. So let's read up on what white metals are about. And it has a little more detail than what you really need. So we will read it and then we'll see the diagrams. It is used mainly for main engine, main bearing and bottom end bearing. This is for your 4-stroke engines. In your 2-stroke engines, you will use it for crosshead bearing, bottom end bearing and main bearing. All three are using thin shell bearings. But in the case of a 4-stroke engine, only the bottom end bearing and the main bearing will be using thin shell bearing. The gudgeon pin bearing is a bronze bush, and that bronze bush is given a little softness by introducing some lead into that bronze. Bronze is basically made of tin and copper. So tin and copper together, they form a very hard combination. To give it a little softness and a better smoothness of the surface, a little bit of lead is also added into that mixture of bronze bushes. So it is called a lead bronze bush. Now who has come? These fellows come at just at 9:40. Harshit Sita. After this, I am not admitting anybody, and class in charges, please do not make any more requests. It is already 9:40. We are under enormous pressure from the office not to allow cadets who are coming late. Up to 10 minutes, I will give permission. It is 9:40 now. After this, I will not admit any more boys. Otherwise, we get a scolding. We get a scolding for allowing boys coming late into the class to be allowed right into the class. So please make sure that you're within time and you will get your attendance only on that case. So we have 36 here, and that this is section C. So there should be actually total of 40. So 4 candidates are absent. Okay. So right now 42, it should, no, 40 and 36 we have here. So 4. So at the end of the class, I'll be taking the attendance and accordingly I'll have to put it up. The office has become very, very tight on us to ensure that the attendance is accurately submitted. So be very careful. I don't know why they have become so strict on this attendance issue. Maybe boys are not performing well, or there have been complaints that the boys are not being adequately coached, or something of the sort has happened. Anyway, so the thin shell bearings, they are used mainly for main and bottom end bearing for the four-stroke engine. For the two-stroke engine, remember, for crosshead, bottom end, and main bearing, all three are using thin shell bearings. What is this now? Okay, the flash layer. These thin shell bearings can be bimetal or trimetal. In other words, there can be 3 layers or they can be 2 layers. But most commonly, there are 3 layers because the intermediate layer is the binding layer. It holds the white metal to the steel complex. In fact, I have been on engines which have worn out white metal and the copper can be seen. Copper. And in spite of that, the bearings can still run for some time. It is not totally off. Only thing, the alignment of the shaft and the clearances, they have to be accurate. You can still run even if the white metal has got worn out. You have to be careful about the lube oil pressure, lube oil condition, lube oil temperature, the clearance, and the alignment. You have to be very cautious about these to make sure that the engine is in running condition. Otherwise, it will be very severe. The topmost layer with a thickness of 1 micron is made of tin and lead, and it is used to protect the bearing from corrosion and dust when not in use. This layer flashes off when bearing is running in period. Now, when the bearing shell is new, it comes to you, it is not going to be having white metal directly because that has some effect with the atmosphere and oxygen, but not really much. So they give it a flash coating, and that flash coating is 1 micron. So it is almost like a surface of a thin paint. And that is used to protect it from corrosion and dust when it is not in use. I don't understand why he says dust, because when you are going to use it, you will wipe off the dust, put oil on the surface, and then fit it in place. So dust really doesn't make so much of a difference, unless he says the dust gets embedded in the white metal. That is possible because white metal is reasonably soft. And to prevent the dust from being embedded into the white metal, you have a coating of tin and lead. And this, within maybe 2 or 3 revolutions of the shaft on that bearing, that flash layer is gone. Under the flash layer, you have an overlay. This is the second layer made up of the white metal. The white metal is the main surface which takes the support of the bearing, and it is tin, antimony, and copper, or lead, antimony, and copper. That is the combination of white metal. It is also called Babbitt metal. You can write it down on a piece of paper. Babbitt metal, Babbitt metal. It is possibly the engineer's name was Babbitt, and he is the one who designed the first white metal for use in bearings, and it has been found to be very good, which is the main component in this type of bearing, and its thickness varies, and this variation of thickness is determined by the designer. He will check how much load it is supposed to give, how much will be the temperature of the oil, what will be the viscosity of the oil, what will be the speed of the shaft. So all these parameters are taken into consideration when determining the hardness of that white metal which is to be used for that bearing. So there is a lot of calculations, mathematics involved in designing of a bearing. It is not only manufacturing white metal and steel and putting them together. So there are thousands, I will say thousands of permutation combinations of white metal constituents. And the designer can order for a special grade of white metal which can be used for the bearings he intends to use for the engines. All right. So that is called the overlay. The interlay is the third layer used as an anti-corrosive layer for overlay. It is 5 microns thick. Now this one also doesn't really going to give so much of effectiveness because 5 microns is almost like a layer of paint. And it is used as an anti-corrosive layer for overlay. Okay. So first you have the white metal. Underneath that surface, you have an interlay. And then you have what is called the lining. This is the one that holds and gives up the bond. It is the bonding device. And it is the lining layer between the interlay and steel back with a thickness of 1 millimeter, made up of lead and bronze, or sometimes copper. Copper is also used. Or copper. Or copper. Mostly I have seen is copper. Lead, bronze, yes, but mainly copper. Because I have seen white metal getting wiped out and then a layer of copper comes there. And it is not totally copper color, a little lighter than copper color, which could mean that it is lead bronze. Because ultimately bronze is also copper. Bronze is copper and tin. So bronze is copper, tin, and lead. This is the same material that is used in the bush for the gudgeon pin. Underneath this lining, you have the steel back. This is the mild steel, or not mild steel, it is a steel, alloy steel. It is definitely a lot tougher than mild steel. Now, this is the diagram to show you, it's an expanded diagram. It is not in these proportions what you see. It is definitely much thinner. But these diagrams are made to give you some idea of what is a thin shell bearing. Now, in the extreme right side, what you see is a steel back, and underneath that, you have an aluminium bonding layer. So instead of copper, here they are using aluminium. And on top of this, they are using an aluminium bearing alloy. That means it is a mixture of some other elements which he has not specified, but the main constituent is aluminium. Aluminium is also a soft metal, and here they can be possibly used, but on board the ship, we have not used such bearings with aluminium as the surface. We have mainly used white metal, but it keeps your mind open that white metal is not the be all and end all as the material used for a bearing surface. So here he can use an aluminium bearing alloy. In some cases, you have lead bronze also. But on board the ships, most of the bearing, I would say 90% of the bearings are white metal bearings, white metal lined bearings. So this is your thin shell bearing where it has an overlay. And under the overlay, you have the nickel barrier, which is supposed to be anti-corrosive, prevents corrosion. Underneath that, you have the copper alloy. This copper alloy, this one is 5 microns. It is as good as nothing. Okay. And then you have the copper alloy, which is binding the white metal to the steel back. All right. So that is how the thin shell bearing is utilized. Now, this is the bearing with cosmetic tin flash. Cosmetic tin flash means this is the cosmetic tin flash, which is going to prevent dust. I don't understand where dust comes in. Dust and oxidation from atmosphere. Which is, see, these bearings will come very well wrapped, very well sealed from the atmosphere. So this issue about having a tin flash layer, I have not experienced it, but the books, the literature says they have it. So we'll have to assume that, well, literature is strong. When you go on the ship, this flash layer will not have much of a bearing to you. What will have a bearing is the white metal overlay, then the copper bonding material, and the thin and the steel backup. The steel backup is of special grade steel. It is not ordinary mild steel. It is definitely a lot stronger than mild steel, which means it has got some alloy steel. It has some amount of springiness. If you try to hit it, it will have a springy effect. Next, nip. The difference, now nip and crush mean the same thing. So it is actually the extended part of the bearing shell which helps in compressing it and ensuring that the bearing shell sits very tightly on the keep of the connecting rod and the bottom keep. So when they are fitted together, initially the diameter of the shells together, outside diameter, is little more than the inside diameter of the connecting rod and the keep when they are assembled together. How much more? Maybe a few hundredths of a millimeter. So what happens? So when you fit the bearings in place, that is a little protrusion of the bearing shells. But when the keeps are put together and the bottom end bearing bolts are tightened hard, this extended part of the shell is crushed or it is compressed within the elastic limits without causing any deformation. So this helps in creating a force on the curved surface of the shell to improve the frictional resistance of motion between the shell and the entire cross bottom end bearing housing. So when it is working, the shell will not rotate inside. The whole idea is to prevent any rotation or looseness of the bearing shells when it is working. Okay. If you do not understand, please put it up on the chat column. I will immediately address your doubts. The difference of peripheral length of the bearing over its housing is called nip. It should be positive to ensure an interference fit. That means it's a compressed fit. And this is also referred to as crush of a thin shell bearing. The thin shell bearings have a wall thickness between 2% and 2.5% of the journal diameter. Now, this is a thumb rule which you will have to remember, because at any point of time during your oral examination, this is likely to come up. What would be the thickness of a thin shell bearing for a shaft diameter of, say, 40 centimeters? What will be the thickness of that shell? That shell means the steel backup, the copper inlay, as well as the white metal. So the entire thickness, what will it be? It will be 2% to 2.5%. That means for a 40 centimeter dia shaft, it will be 400 millimeters. 400 millimeter, 2% is 8 millimeters. Between 8 millimeters and 10 millimeters will be the total thickness of that thin shell bearing. All right. So these are little bits of knowledge which you will require in your multi-choice questions. In your normal written examinations, they are not likely to come up, but in your multi-choice questions, these type of questions will come up. The thickness of a thin shell bearing of a journal shaft of 500 millimeters is 1 to 2 millimeter, 2 to 3 millimeter, 2.2 to 2.5%, 2.3%. You have to pick the dimension correctly. So remember, it is between 2% and 2.5% of the journal diameter. I hope you'll remember. Next is the maximum and minimum top clearance in the shell. Now, when the shell is fitted and the shaft is there will be a clearance on top. On what basis is this clearance determined? Okay. The top clearance is fixed and results from a summation of the housing bore, shell wall thickness, journal pin diameter tolerances, and for main bearings, the deformation of the bed plate from the stable tensioning force. Now, these are some of the some of the parameters which are taken into consideration to designate what should be the clearance between a thin shell bearing and the shaft or journal diameter. So you need to take all this into consideration. That means what should be the shell thickness, what should be the diameter of the shaft, what should be the distortion of the transverse girder. If it is a main bearing, you see the main bearing, when it is tied up with the tie rod, there will be a change in the transverse girder. The transverse girder may bend a little. If it bends, the whole bearing inside will also reduce at the top. So if you remember, I had told you that the tie rods in a bed plate, they have to be as close as possible to the central axis of the crankshaft. And this is intended not to cause bending of the transverse girder. If you bend the transverse girder, the bearing shape also changes. So this has to be taken into consideration when they are determining what should be the clearance between the shell and the journal shaft. Okay, now here is your diagram which shows you how a thin shell bearing is installed. Now the lower half is installed in this position and it protrudes a little bit more than the hemisphere of the housing. The hemisphere of the housing is this lower piece over here, and the upper piece is part of the connecting rod. Okay. So when the two of them are put together with the bearing in place, there will be a gap between the faces of the bottom keep and the connecting rod. This gap is called the crush height, and it is the height which has brought down from whatever it is to zero, because that is the time when the two tie bolts, or when the two bottom end bearing bolts are tightened to the required torque. So in tightening the bolts, this gap will vanish. It will disappear. In other words, the material which is protruding here will be compressed. This compression force ultimately results in a force along the curvature of the bearing shell at the bottom, as well as the curvature on the bearing shell on the top. The top half over here is not shown, but it is existent as you've seen here over in this diagram. So when these bolts are tightened, the maximum force is exerted in radial direction to increase the pressure of the shell against the keep. So this prevents the shell from rotating inside when the engine is working. It is a very, very important issue with thin shell bearings. And one of the main reasons is the thin shell bearings over here, you are seeing only the lower half. All right. The upper half shell is different from the lower half. And Ketan Kumar Sinha will tell us what is the difference between the lower half and the upper half of the thin shells. Ketan Kumar Sinha.
Yes, sir.
Now tell me, what is the difference between the lower shell and the upper shell in a bottom end bearing, thin shell bearing? I have to keep myself awake, so I need communication with you. Otherwise, this constant monologue makes me very sleepy. Come on, Ketan, give us an answer. It doesn't matter if you're wrong. If you're wrong, it is for me to correct you and help you out.
Sir, in the upper shell bearing, there is a oil hole.
Okay. Very good. Why? What is that oil hole for? Hello?
Yes, sir. Yes, sir.
Yes. Go ahead.
Sir, for lubrication.
Of what? For the bottom end bearing?
Yes, sir.
Yes, sir. Just I put a trap for you and you fell in it.
Sir, Gajan
It
pin.
is.
Sorry, sir. Gajan pin.
Yes, it is for gudgeon pin.
Gajan
Right.
pin, sir.
Yes, correct. So that oil hole in the shell must match the oil hole in the connecting rod. And then only the oil can go to the gudgeon pin. Now, if the two shells rotate, then that oil hole of the shell will change its position and the oil hole to the gudgeon pin is blocked. So your gudgeon pin, piston, everything will fail. So it is very, very important to ensure that when the shells are fitted, they are fitted in the correct position and tightened to the required torque so that the oil hole in the shell matches the oil hole in the connecting rod. Okay, good. Ketan, now you kept me awake also. Very nice.
Yes, sir.
Otherwise it's very not easy to constantly talk and stay awake because I can't see you. I can only see my laptop screen, which is very difficult. So I'm waiting to get back to our original procedure of classes. Okay, so you have everybody, I hope, has understood the arrangement of a thin shell bearing and what is crush and what is nip. It should be very, very clear to you. Next, medium speed engine. Now that is finished with thin shell bearings. Let us go to couplings and reduction gears. Medium speed engines, because their speeds are much higher than the propeller, they will need a reduction gearing. This reduction gearing is also coupled with a flexible coupling. This flexible coupling helps to accommodate small amounts of misalignment it takes up some amount of shock loading, and it eliminates or reduces transmission of vibration. All of you, or rather most of you, will have seen a flexible coupling. In fact, in the engine room, every item has got a flexible coupling. Whether it is a small pump, whether it is a piston cooling pump, whether it is your compressor, everything has got a flexible coupling. This flexible coupling is very simple in most of the cases. What is it? It is just got a rubber pad between the driving shaft and the driven shaft. So what is being turned is actually pushing onto the rubber pieces. And those rubber pieces are ultimately pushing onto the driven shaft. So if there is a sudden torque, that torque will impact on the rubber, which is compressible. So it takes up any shock loading or sudden compressive forces, and it does not transmit that force to the driven member. Similarly, if there is any misalignment within small limits, if the shafts are misalignment, the bearings which are supporting the shaft will not be under undue loading. So the bearings will still remain. If the shafts are rigidly coupled and then there is misalignment between one shaft and another, then the bearings will be getting damaged very quickly, because ultimately the shafts will be bent, and as they rotate, they keep bending in the opposite directions, and the bearings get worn out or they will get damaged. But with a flexible coupling, it can take some amount of misalignment, it can take some amount of shock loading, and if the driving shaft is vibrating, that vibration will not be transmitted to the driven shaft. So this is what a flexible coupling means. And this is used on almost every drive in the engine room. Anything. You will see the flange of the motor and the flange of the pump. In between, they have a rubber pad. You have probably seen it in your home if you have a pump in your ground floor at the basement where you have an electric motor and a pump. And the coupling flange over there, it is hollow. And inside that hollow space is a rubber disc. That rubber disc has got 4 holes. 2 holes are for the motor pins and 2 holes are for the pump pins. And the disc in turn transmits the forces from the electric motor to the rubber pad, and the rubber pad transmits the forces to the pins of the pump. So that itself has some amount of shock absorption. Apart from shock absorption, if the 2 pins are little misalignment, it doesn't make any difference. The rubber will take the shape and accordingly transmit the torque. Similarly, if there is any vibration of one shaft, the vibration to the other shaft will not be transmitted. Actually, it will be transmitted, but it will be damped out considerably. Total removal of vibration will not be there. There will be some amount of vibration transmitted, but definitely it will be reduced to a large extent. Okay. Mechanical couplings, some transmission of vibration is there, but in hydraulic and electronic or electromagnetic, it is damped out completely. Okay, so you know what is a flexible coupling. It accommodates vibration, it takes up shock loading, and it can take up some amount of misalignment. All right, okay. Flexible couplings may be mechanical, hydraulic, or electromagnetic. Most common is the mechanical devices, which we will discuss just now. Mechanical couplings incorporate reduction gears to save space. Now, if you are going to use a flexible coupling and you want the RPM also to be reduced from 500 to 100, you will need to have a reduction gear also. So the gears are very close to the couplings, and the couplings are very close to the clutch. So in fact, the coupling and the clutch are made together, and the gearbox is a little to the side. As much as possible, they try to make the space as small as possible. Otherwise, it wouldn't make sense to have an engine and to have your propeller shaft and a huge, big coupling clutch gearbox arrangement. It has to be a little small. So that is why they are made together. The clutch and the coupling are made together. The gearbox is a little separate, because the gearbox has to have oil in it. The clutch and the reduction coupling don't need oil. All right. Okay. Flexible coupling and reduction gear. This consists of a driving member and a driven member. The driving member is generally the crankshaft of the engine, and the driven member is the propeller shaft that leads to the propeller. Okay. My water bottle. Okay. Engagement involves how does the driving member engage the driven member? It involves the inflation tube with air pressure. So, moment there is air pressure, it inflates the tube, and the tube makes contact with the driven member through a Faraday lining. Faraday brake lining is what gives the grasp. If you cannot have metal to metal, it will slip. So you must need a frictional material, and the best frictional material is Faraday brake lining. You might have ridden on bikes, you might have seen car brakes also dismantled. So inside there, the surface which rubs against the drum to have the braking effect is called Faraday brake lining. Faraday is possibly a trade name, but it is generally made of asbestos and other compounds. Let me make a note. I have to find out exactly what is the material. Material for Faraday lining. I know it is asbestos and other material, but what are the material? Lining. Okay. Okay. So this brake lining is against the inflation tube. Moment it inflates, it engages. It is something like your car brake when you or a motorcycle brake. You're more familiar with the motorcycle brake. So when you pull the brake, what happens there is the brake lining comes and makes contact with the drum, and then there is friction, and this friction reduces the revolution of the wheel. So that's the same idea. Now here, the brake lining is made to engage and it keeps it pressed. So when it turns, the whole wheel will turn. Okay, it is not for stopping, it is for actually turning. It is like a gripping device. Controlled air passage through the shafting to the tube. Tube material is made of high-grade spring steel, which is 3 millimeters in thickness. Coupling is through rubber blocks between the members. Rubber or springs. Springs can also be used sometimes in flexible couplings. So it is not an unusual feature, but springs are more difficult to control. And if something goes wrong, it becomes a major problem. Whereas rubber blocks are simple blocks and nothing can go wrong almost. At the most, the rubber blocks can get damaged. But springs, if they break or they come off, they can damage the other components also. So that is why rubber blocks are more preferred in couplings. Next is this flexible coupling. If there is an emergency, then how will that emergency coupling arrangement in event of tube failure takes place? This is a question for you. Now you have, I'll give you the diagram just now. The inflation tube, which is 3 millimeters thick, is inflated, deflated, inflated, deflated umpteen number of times to engage or disengage over a period of time again. Now, in case that the tube ruptures, it will not work anymore, it will not inflate anymore, it will not grip the shaft anymore. So how will you turn the propeller shaft and bring the ship to shore? That is the question. That's why I've written cadet's question. If the tube ruptures, how will you bring it to shore? Now here is the diagram of your flexible coupling only and clutch system. The gearbox is not shown here. Okay. Now on the left side, what you see is the propeller shaft end. Okay. Now this is a flange with a rigid coupling. A rigid coupling means it has got what is called fitted bolts. Fitted bolts are different from normal bolts, and the difference is that there is no clearance between the shank of the bolt and the hole through which the bolt fits in. There is no clearance. It is a fitted bolt. and they are used in propeller shaft drives mainly, in some foundation bolts of machinery, and wherever there is absolutely no relative motion permitted. Okay. So now on this driven shaft or propeller end shaft, you have another star-like structure, and this is that star-like driven member. You see, this is the piece what you see here, and it has got blades. These blades or teeth, whatever you want to call. So these teeth are at a certain distance from each other. All right. And if the propeller rotates, this whole inner piece will rotate. Okay. Now, outside the star, you have another drum which is free floating. Free floating means it is not immediately held by any other shaft or other device. It is free floating. And inside the free floating drum, let's call it drum, free floating drum. So on the inside, you have teeth which are exactly the same size as the one that is already there in place for the propeller shaft. Now, in between the teeth, you have rubber blocks. All right. So these rubber blocks are what is between the teeth. So the teeth will never touch each other. It is always the rubber blocks that will come in the way. And in fact, if you try to remove the driven shaft, it will go and compress the rubber shaft, and at the same time tell the other rubber block to push and make contact with the other teeth. Okay. Now this drum on the outside has got a very smooth surface, round. And once it is fitted there, if you can grip that surface and rotate it, you can rotate the propeller. So the next requirement is the clutch, which will catch on this drum, what you see, and help it to rotate along with the engine. This clutching device is fitted on the engine-driven shaft, not on the propeller-driven shaft, but engine-driven shaft. Okay. Now, this clutch consists of a large drum. This is a large drum that you see, and it is hollow on the inside. All right. It is fitted to a flange, which is fitted as the engine crankshaft extension. So this side, you have the engine extension, and within the shaft, you have a hole drill to allow for the air to come in. If you see the air, it comes in there, comes up there, and comes into this inflatable tube. And when air is allowed to be pumped in through that pipe, the inflation tube expands, and the Faraday lining will make contact with the top surface of this curved cylinder drum and grip it. So moment it is gripped and it is then rotated, it will also rotate the inner shaft, which has got blades, and it is turned by the rubber blocks. Okay. Now, when you want to engage the clutch, you simply blast air through this point, it inflates and it grips the clutch. And it is become now one shaft. Okay. Now, if you want to release the clutch, all you need to do is vent this pipe. Moment you vent this pipe, immediately the pressure will drop, so much so the inflatable tube, which has some amount of springiness within, will contract and allow the air to go out without any problem. So it is declutched. Any questions? No questions. Khalid Yahya Ahmed. Khalid Yahya Ahmed. No response. Okay. Nilesh Kumar. No response.
Yes, sir.
Who's this? Nilesh Kumar.
Yes, sir.
Okay. Nilesh Kumar, have you understood what I've said about the clutch and the flexible coupling?
Yes, sir.
Okay.
But sir, can
Now
you
that you
explain the
have
clutch once again, sir?
see, you are not paying attention.
No,
The
sir, due
clutch
to network
consists.
problem.
Okay. The clutch consists of a drum, a hollow drum like that you see, and it is fixed rigidly to a flange. And that flange is part of the shaft which is coming out from the engine. After this, you will have a flywheel, and then you will have the engine. So moment air is passed through this passage here, it goes and inflates the tube. The tube is on the inside of the drum and it is about 12 to 15 inches wide and about 2 to 3 inches height. The Faraday lining will be about 10 millimeters, a maximum 10 millimeters. So the clearance between the lining and the drum is barely 3 to 4 millimeters, which speaks of a very, very high level of alignment between the driving shaft and driven shaft. If the driving shaft and driven shaft are not aligned, that means there will be no clearance all around. At some portions, it will be touching. That should not happen. So when the tube is inflated, the tube expands. When the air is passed through and the tube is inflated, the Faraday lining makes contact on the drum. This is the driving member and it grips that entire drum and rotates it. And this helps to rotate the propeller shaft also. When you want to release the clutch, you need to only vent the air from the pipe and the tube goes back again to give a clearance between the Faraday lining and the drum is now free. So the propeller can rotate on its own without having to rotate the engine. Now the engine can be started in the reverse direction because there is no load on the engine. It has declutched the propeller. So the engine can start very easily. It will take less of air. You can check whatever is required of the engine. You can run it as long as you want. So these advantages as a medium speed engine are available for such ships. All right, so let's move on. Now we have spoken about the clutch and the flexible coupling. The flexibility arises between the driving member and the driven member because neither of them are actually touching each other and they are loosely connected by means of these rubber blocks. So this can go out of alignment, this can remain in alignment, and then it has to move on. Now let us look at the gearboxes. Now here in the first diagram, you have two engines. Sir, can this Faraday lining be used to reduce RPM of propeller or to brake the ship? Kartavya Singh, good that you have put up this question because during the sea trials, I explained to you what is crash stop. During crash stop, yes, this is what you do. This Faraday lining is what stops the propeller from rotating in the ahead direction. And then once the propeller stops, the clutch then helps to rotate the propeller in the opposite direction. In the crash stop or the sea trials classes, when I told you, the crash stop is just one button which you press. After that, the whole program is computerized. First, what happens is the declutching of the engine takes place, the fuel is cut off, and the engine is stopped. But the ship, on having its momentum, propeller keeps turning. So that piece over there, this shaft will keep turning. In other words, this whole thing will keep turning because the driven member, which is the part of the propeller, will keep this drum rotating. But the clutch has disengaged. So the engine will not be rotating. Engine will stop very quickly within few seconds. Then what we do is reverse the engine and restart the engine. Once the engine is restarted, then this side of the shaft is rotating possibly anti-clockwise and this shaft is rotating clockwise. So the two of them are rotating in opposite direction and that is the time when the clutch takes hold. And that is the time when the air pressure to the clutch is passed. So initially when the Faraday lining rubs against this outer surface, there will be a lot of smoke, a lot of sound, and maybe vibration of the ship and things like that. And smell also, a burning smell will come. After some time, the friction between the pad and that propeller shaft drum will help to stop the propeller from rotating. And then the propeller, once it stops rotating, because the grip is on the Faraday lining, it will require it to rotate in the opposite direction. And as it starts rotating in the opposite direction, the speed of the engine increases. That means the propeller is rotated very fast in the astern direction to further cause a braking effect of the ship. That is what you have said over here. Kartavya, is that clear now?
Yes, sir.
Okay. So now in the gearbox system, you have two engines here in the first diagram, 1 and 2. Both the engines are reversible and they both have clutches and they are running one propeller. So out at sea, you can run both the engines at full power to give the maximum thrust by the propeller onto the thrust shaft. So that possibility is there. In a harbor or near the port, when the ship is going to be docking, you need very frequent changes of direction for the propeller. Ahead, astern, ahead, astern. And now it is not advisable to keep stopping and starting the engine because you want ahead and astern. So what they do, they put one engine as astern direction running, and one is an ahead running direction. And all they do is disengage one clutch, engage one clutch, disengage one clutch, and engage one clutch. So in that process, you can keep changing the direction of rotation of the propeller. So this helps in not having the air compressors continuously filling up the air bottle and having wear and tear of the engine much more by stopping, starting each time the bridge or the captain wants the ship's propeller to rotate in opposite directions. So this is the arrangement for not requiring the engines to stop. In fact, all medium speed engines don't require the engines to stop, and the operation of the propeller is changed by changing the clutch operation. Clutch operation also consumes air, but definitely maybe 1/10 of the air consumed in starting of an engine. So much. It's a big difference. So that is why they have done away with the normal two-stroke engines in many cases, and they are using clutches. In the second diagram, you have a single engine which can be used in port for generating electricity or running your cargo pumps. All right. So this one has only one engine, one main engine, and the propeller shaft is along the central axis of the ship, and the engine is slightly offset, and the engine can be clutched onto the propeller shaft, and then propeller shaft can rotate as required. In port, you can declutch the propeller shaft and use it to run an alternator or generator to generate electricity in the port and do away with one diesel generator. Normally you have 3 auxiliary engines. Now if you have this arrangement with the main engine, you can knock off one auxiliary engine because it will not be required. The advantage here is the main engine, which is burning fuel oil, is producing electricity at a much cheaper cost as compared to the auxiliary engines which are producing electricity at the cost of distillate fuels. All right. So in port, you can use this to run your alternator or electricity generator, or it can be also used with an extended shaft to run your cargo pumps. Cargo pumps are large pumps, very large pumps, which pump the oil from tankers to shore. So you need a large pump. So these pumps, which are delivering the oil from the ship to shore, need enormous amount of power. So that power is now coming from the main engine itself in port. So whatever the ship owner has invested his money in, he is getting the returns. Okay. In the next diagram, what you see is actually the same diagram. Here you have one engine which is running continuously only in one direction. With that one direction rotation, the propeller can be rotated in ahead or astern direction. How is that? Okay. You have 2 clutches with 2 gear shafts and 1 pinion from the main engine. So when the engine pinion is rotating in the direction as shown, this one will rotate in astern direction. And if your clutch is engaged for that particular one, which is B, the propeller is going to run in this direction. Okay, because this is in this direction, this is in this direction, this is in this direction. All right, now you want, this is astern running. Now you want ahead running. So what you do, come to the right hand side diagram. you disengage one clutch and engage clutch A. Previously, B was engaged, it was running in the direction as shown. And when you engage the upper clutch and remove the lower clutch, the propeller rotates in the opposite direction. So these are the basic arrangements in the gear systems of a medium speed engine. One important issue is the gear system here is called herringbone gear. I'm leaving it to you to find out why and what is herringbone gear. I'm not going to answer this question. Let's go on to exhaust valves. Modern exhaust valve designs, they involve separate caged valves which gives ease of maintenance and no requirement of removing cylinder head to dismantle the valve. The earlier valves, they had valves which were fitted from underneath the cylinder head. So every time a valve had to be opened out, you had to remove the cylinder head. But now only the inlet valve is fitted from below because the inlet valve rarely requires attention as much as the exhaust valve requires. So the exhaust valve is made in a way where there is a cage. The cage is intended to allow the hot gases to pass through. So this entire valve with the cage is installed in the cylinder head. And if required for overhaul, you can conveniently remove the exhaust valve without disturbing the cylinder cover. All right. So that is the modern concept of exhaust valves in cylinder heads. The entire valve can be taken out without having to remove your cylinder head. Okay, just give me a minute, please. I will go and get my water bottle. My water bottle is not here. Okay, I am back with the water bottle. Let me drink a little water and I will restart again. Oops. You can read it in the meantime while I sip a little water. My throat is hurting. So in these exhaust valves, which are separately caged and can be removed from the cylinder head, all the connections, cooling water, is exhaust, how the exhaust passage is made is also made very simple. The cooling water passage, they have simply a pipe with two rubber rings which can be fitted in the sockets without any flanges, without nuts and bolts. Similarly, the exhaust passage, it has got what is called expansion bellows. Write it down. Expansion bellows. And find out what are these expansion bellows. At least they are made because the temperature variation from room temperature to 350 degrees centigrade causes a expansion contraction of the pipe. So instead of using a pipe, they will use an expansion bellow. The bellow is soft, it is compressible. At the same time, it can take very high temperatures. So the exhaust gases pass through the expansion bellows. Material of the valve must resist high temperatures and corrosive wear, corrosion and wear. Okay, both are actually synonymous. So what material you use? Stellite. Stellite is a material which is a mixture of cobalt, chromium and tungsten. CCT, cobalt, chromium and tungsten. And this stellite is generally used for the seat of the valve. The valve is made of something else which is also very hard and very little of ferrous material is there. But the seat of the valve, which is subject to maximum wear, is made of stellite. That's the most common material used. And this stellite has a mixture of cobalt, chromium, tungsten, and some more other items too. I will show you a chart just now which will give you an indication of what they're made of. Other than that, the design of the valve is sometimes tulip shaped. What is a tulip? Tulip is the name of a flower. Okay, tulip is the name of a flower. And that bulb of a flower is similar to the shape of the exhaust valve. And it is made that way to improve the strength of the disc of the valve. The valve itself has got a disc and it has got a spindle. So the disc portion may bend. So to avoid it from bending, it is made thicker. But there is a limit to how thick it can be made, because if it is made thicker, then the thermal stresses that arise will become more, and possibly there will be cracking of the valve. So there is a limit to how thick the disc can be. It has to be strong enough to bear all the stresses, and there are a lot of stresses which we will come into just now. Then you have a different design by the MAN manufacturer, and it is called a W seat. You see, when the valve is ground on the seat of a cylinder cover insert, it seats very well. But when it is running under a temperature of 350 degrees centigrade, some amount of distortion takes place. This distortion takes place because underside of the valve is very hot, because that takes part of the combustion spaces, and above the disc, it is not so hot. So the bottom part of the valve will expand more. So moment it expands more, then the seat angle changes. Moment the seat angle changes, there is possibility of exhaust gas leak. So MAN has come out with a design where when it expands, it will make contact and perform the seating. And when it is cold, again it will perform the seating. So it avoids any form of leakage of the valve when it is working. Okay. Now here is the diagram of the inlet valve and the exhaust valve. See, the inlet valve, it is fitted from down below, and it does not require any cooling arrangement, because the air which is coming into the valve and going into the combustion spaces is at 40 degrees centigrade, and it provides the requisite cooling of the valve itself. So there is no extra water cooling arrangement required for the inlet valve. Whereas the exhaust valve, where the hot gases keep flowing outwards, the entire valve gets very hot. So you need cooling water. So this void space that you see inside allows for cooling water to come in or go out from this region. One section is shown, and this region could be inlet or outlet, which we have not particularly specified. Let's have a look at what he says. 19. Oof, I can't see. My eyesight is not so good. So this is your exhaust valve, and it is seated in a way with a cage. The entire cage can be removed, you see. The whole cage. This nut has to be opened. This piece has to be removed, and this locking or this pipe, short piece, will be removed. And then the whole piece can be removed once you remove the main foundation bolts. Foundation bolt removal alone is not enough. You'll have to remove this piece here. Moment you remove this piece, then this little short pipe will not be an objection to this one going upwards. So it raises the entire piece. This cage over here has got an insert over here. So this insert is resting on the cylinder cover. So the whole insert is removed upwards. Whereas in the inlet valve, you will see the valve is touching the cylinder edge. Actually, there should be an insert here. He has not shown the correct diagram. So that insert obstructs the passage of removing the valve. Whereas in the exhaust valve, the entire valve can be removed. To remove the inlet valve, you have to remove the cylinder cover and take it down from below. Now, I have a question for you. You see both the valves, they have got two springs each. One is an inner diameter spring, one is an external diameter spring. Why should there be two springs? Why can't I use one spring with adequate strength of the two springs? Should be enough. So why two springs are used? You rack your brains and you let me know at some stage. Let's move on. Now, design of the exhaust valve. See, the first one, what you see is something like a tulip-shaped valve. It is made a little thick over here, and it is definitely much stronger where bending forces can take place on the disc. The disc can bend because there are enormous amount of forces acting on it. So this is good for mechanical strength. But when it comes to thermal issues, the temperature here and the temperature underneath the valve will be considerably different. So in the process, if there is a thermal stress, there will be a fracture taking place. If it gets fractured, then the whole valve is useless. So it is a compromise between how thick it can be and what will be the thermal stress it can take up. Now here is the standard valve. This standard valve at the top of the stem or top of the spindle has got a recessed portion. This recessed portion is what helps to hold the valve and pull it up by the springs. Okay. Now what you have is a spring carrier, and this carrier, hole in the spring carrier is a taper. Okay. And that taper conforms to the taper of these collets, which are in halves and can be fitted in the recessed portion of the spindle. So once they are fitted, the spring carrier can be lifted up and it will hold the two together. At the same time, it will hold the valve up. So it is a locking device cum holding device, both. So the spring carrier, under which there are two springs, will force the spring carrier upwards. But the spring carrier has got a tapered passage or hole which will lock into the collets which are in two halves. If you are to remove the valve, you will require a special tool which will compress the spring carrier downwards and compress the springs also. Then the collets can fall out. Moment the collets fall out, the spring carrier can be removed from the top of the spindle. So it is just a means of holding the valve in position by the means of springs. In the right hand side diagram you see is what is the new valve, absolutely new valve. And this new valve, you will notice that the seat angles of the valve are different by about 1 to 2 degrees only. This 1 to 2 degrees only is intended so that when the valve is actually working in place, the bottom part of the valve will expand more as compared to the top part. This goes for any valve. So before it expands, it will go and make contact at the portion where there is showing a gap because of the difference in the angle. You see in this figure, there is a gap over here. So it is making contact only at this point here, at the inner edge of the seat. So when it gets heated up, the expansion of the lower portion will cause the valve disc to bend in a way where it gives complete contact of the seat and gives more or less 100% integrity of the combustion chamber and seating of the valve. All right. Now the same principle what you see here, this is only possible during its new condition. Over a time period, if you do some grinding, that angular difference will vanish and the valve will continue to run no matter what, but it will not be so good. So to accommodate this facility, MAN has designed an insert with a little clearance here and a groove here. So it has got a groove here and a clearance here to ensure that when the valve is working under a high temperature, this portion will expand to make contact at this rim, and at the same time it will be making a contact over there. So the entire seat will provide the sealing, and there will be no leakage of the gases. So these are the designs of your exhaust valves, and if at all you are required to explain, you can explain. Okay, there is much more to it, but we can't afford to go so much in depth. Otherwise, the entire course on medium speed engines will go in only valves. So I have skipped a lot of information to ensure that whatever little is required, you are aware of. If you want more information, more knowledge on this subject, you will have to read beyond my program, my notes, or my PowerPoint programs. I cannot include everything. Then it will become, each program will become 100 plates. Okay. Now, exhaust valves are subject to the following stresses. What stresses? One is the temperature gradient or thermal stress. All right. Next one is seating pressure due to gas pressure. That means when the combustion takes place, there is a gas pressure on the valve. So that valve disc will be under a lot of pressure. Apart from these gas pressures, the springs are pulling up the valve. That force itself is considerable and it exerts a pressure on the seat of the valve. Okay, this is called seating pressure due to closing of the valve. The closing of the valve is done by the springs. Next is manufacturing processes, which is called residual stresses, which is very rare. Unless you give the valve for reconditioning, the residual stresses will not be there. How does the residual stresses arise? If some part of the valve is overheated and another part is not heated, you will have residual stresses. Like welding, to deposit metal on the seat with stellite, you need to have stellite iron rods or welding rods. These welding rods are very costly. So these welding rods are used to deposit the metal on the seat. And thereafter, they are used on the lathe machine to smoothen them out. Okay? Once it is smoothened out, they can be used. But then when you weld, you are always generating some amount of residual stresses in that component. What you require to do is actually heat that entire valve with the seating to a very high temperature, then allow it to cool gradually. This process is called annealing. But normally, if you give it for residual, for reconditioning, these fine processes are not done, and the fine processes are only done by the manufacturing companies with the right temperatures, the right conditions, etc. The local manufacturer may give it some annealing, but that annealing does not compare with what the original manufacturers do. Apart from this, the valves also subject to some stresses. If the cylinder head gets distorted, if the shape of the cylinder head distorts, then the entire alignment of the valve with the seat will not be there. Okay. What are the material property requirements of exhaust valves? It must resist hot corrosion. Hot corrosion is a mode of corrosion by which sodium and vanadium play a large role. And this sodium and vanadium, when they are burning, they form very complex salts. These salts deposit on the valve seats, on the valve stems, in the exhaust passage, on the turbine blades, everywhere, wherever the exhaust passage is there. And these deposits are very, very corrosive if they are in the liquid state. But deposits are generally in solid state. Okay. Now, some of these salts are not some, all of them are called sodium vanadates. Vanadates. There are a total of 8 different sodium vanadate salts. All are having a little different molecular construction. And the most basic one melts in the region of little more than 450 to 540 degrees centigrade. The others melt at a higher temperature. Okay. Now, if the salt which is deposited on the seat of the valve reaches a temperature where it melts, in the melting condition, it is very, very corrosive. It is literally so corrosive that a valve within hours, within few hours, it will be eaten up or corroded to an extent beyond recognition. I will show you a diagram which I've shown to the other sections also of the example of hot corrosion on an exhaust valve. Okay. Okay. Ketan, can I see the diagram?
Yes, sir.
Okay. Now see, this is an example of hot corrosion. It looks like a rat has eaten it up. So I have actually had the experience of such corrosion, hot corrosion, and it is largely on account of sodium and vanadium being present in the fuel oil. So in the fuel oil, how does sodium come into the picture? Vanadium is always there in the fuel oil. It cannot be avoided, but the limits are various. Now sodium comes in if the fuel oil is contaminated with seawater. And seawater contamination of fuel oil is not uncommon. It's very common on the ship. In fact, when you take bunkers, your fuel oil will have some amount of seawater in it. Because that barge, wherever it has been, which has brought oil, has probably been in bad weather and some water has gone into the barge where the oil is. So that is how it comes up. So that seawater, when it is evaporated, the water goes away, but the sodium salts, that is sodium chloride, magnesium chloride, calcium sulfate, all are there. Sodium chloride is the largest constituent. So this sodium from there reacts with the vanadium during combustion to form sodium vanadates. And these are very, very corrosive and they cause corrosion to the extent that you saw just now. And that type of corrosion is called hot corrosion. Cold corrosion is corrosion with sulfur. When sulfur forms sulfur dioxide during combustion and it combines with the moisture to form sulfuric and sulfurous acid, and then you have corrosion of the components, that is called cold corrosion. Okay. So material property must have hard seats to resist indentation. Indentation means any substance or any hard particle coming between two contact surfaces will make an indentation within that, and then the gas will start leaking from there. So the seats must be hard enough, and that is why we use stellite. It must also have a low coefficient of expansion to keep thermal stresses low. Moment the coefficient of expansion is large, then it tries to force itself against the other. All right. That means the stellite has a different coefficient of expansion. The valve has a different coefficient. Now, when there is a temperature change, they will be forcing against each other, and it brings about thermal stresses. Next is have fatigue resistance over a wide temperature range. Fatigue failure takes place largely on account of fluctuating stresses. And sure enough, the valve is under a lot of fluctuating stresses and is prone to fatigue failure. But in my experience, before fatigue failure can take place, I find the valve gets damaged, or the seats get burnt, or the seats get corroded. Fatigue failure is a much more remote occurrence for exhaust valves. Good bonding of base metal and hard facing. That means the hard facing which is put on the valve seat must have very good holding strength with the main valve material. That means close coefficient of expansion of base metals and hard facing metals is desirable. Let's put it here. Desirable. Incorrect. Desirable. Okay, never mind. So that is what it is. Next, what we have is, So what is the material used for exhaust valves which are used in residual fuels? In your distillate fuels, you can use this martensitic, austenitic and martensitic without the stellite seating. Those valves are capable of taking distillate fuel. But in the case of residual fuels, you will need this hard facing, because one of the items residual fuel brings about is ash and debris. This debris will create a lot of indentation and damage to the valve. So that is why you use special material for hard facing. So the material used for the valves is mnemonic 80A without hard facing, because the mnemonic by itself is very hard. It be mnemonic 81 also with D-Lero alloy 60 hard facing, mnemonic 81 with Colmonoy 6 hard facing, or you can use stellite also. Stellite is also used for hard facing. The Colmonoy and D-Lero are more recent developments and they are not so common, but they definitely give very good or improved performance of exhaust valves. Now here I have a chart which says what the exhaust valve materials are made of. You see, mnemonic 81 is one of them. You don't have to mug up the entire, this is just to give you a guideline of what the material constituents are there in an exhaust valve. In an exhaust valve, let us consider only the first one, mnemonic 81. It consists of 0.05% of carbon, 0.5% of silicon, 0.5% of manganese, 30% of chromium, 1% of iron. See, iron has got only 1%. Possibility is not even magnetic. If you put a magnetic against the exhaust valve, it will not have no effect. 0.9% of aluminium, and then titanium, it has got 1.8%, and cobalt 2%, and the 65% is nickel. So nickel is a very hard metal. So nickel is a constituent for your exhaust valve to the extent of 65%, and your chromium is 30%. So it is as good as having a nickel chrome valve. These are very costly. So you need to take a lot of care of your engines where the exhaust valves are concerned. Otherwise, your ship owner is going to go bankrupt very fast. Okay. So there are other metals also which I have shown, and none of them have got a very high level of iron. See, this one, 2112, and it's got 11% of iron. That means total of 89% or 88% is remaining other materials. Balance. Here it is aluminium. Very strange. This must be a very simple valve. It's got balance is aluminium. Or is it, what is it? Al, aluminium. Yes. Very, very unusual this valve is. I think it must be used for some other purpose. I never heard of aluminium being used as an exhaust valve. Anyway, these are not of our relevance. Our importance is mnemonic. Okay, so let's move on. Now here we have now the V-type engines. Your V-type engines. Now we are going on to our V-type. V-type engine consists of two banks of cylinders. That means each one is called a bank. A bank means a row. Wait a minute, what is this? Divakar, sir, what is this tool called? I mean a specific name. Which tool?
Sir, the tool in the exhaust valve spring that it is used.
Okay. Yeah, that tool is just an iron rod, which is a lever, which gives you the mechanical advantage to, it's like a lever. And the end of the lever has got a hinge. And on that hinge, you have a circular iron ring, all right? And at the end of that ring, you have a means of locking it onto the cylinder head, all right? It is above the crosshead. Now, this tool, when you use to press it, that ring helps to go round the spindle and compress down on the spring carrier. It presses down on the spring carrier, and then the spindle comes up and the collets will fall out. Moment the collets fall out, the spring carrier can be slowly released with that tool, so it comes out. That is the only way you can dismantle the springs to remove the valve from bottom if it is an inlet valve. For an exhaust valve, that exact exhaust valve has to be put on a stand, and then a similar tool has to be used where the spring carrier can be pressed down and allows the spindle to come up from the middle. So moment that happens, then the collets are accessible and those collets can be removed, and then the spring carrier can be removed. The collets are used to lock the spring carrier in position while the springs are under compression. Otherwise, there is no other way. Okay. So when you go to workshop in college, go to those tables where there are a lot of valves. There are cylinder heads, and there the valves are still there with their collets, their springs, and I think the tool is also there. Normally, the tool is missing because nobody realizes that this is an important tool. It looks so simple, but that tool is used to dismantle cylinder head valves, inlet as well as exhaust. There is no specific name. You can say cylinder head valve removal tool. That's the best name I can give it. Cylinder head valve dismantling tool. That is more accurate. Okay. Okay. Now we
Yes, sir.
have, okay. So you can go on Google once and check it out. I wish we were in workshop. We could have shown you the instrument to dismantle the cylinder head valves. In any case, let us have a look. How much time we have? Oh, not much time. Okay, so this is your V-type engine, and the V-type engine has two units fitted onto one crank pin. In other words, one throw is running two pistons. So when this rotates, this piston is reciprocating, whereas this one is also reciprocating based on one crank pin. And while this one over here is seen at TDC, this one is yet to go on TDC. When this point is over here, then this one will be at BDC. So when this one comes here, then only this piston will be at TDC. So two connecting rods are connected to one crank throw in a V-type engine. The angle between the two can be anything from 30 degrees to 90 degrees. And on either side of the V-type engine, you have the camshaft drive. The camshaft is driven by an idler. You see, this is an idler wheel, and this is a crankshaft wheel, and it rotates the idler wheel, which rotates the camshaft. So the camshaft is along this axis on this side, and along this side on this axis. So this camshaft will be operating all the fuel pumps for these cylinders. Similarly, this camshaft will be operating all the fuel pumps and push rods on this side. One difference this engine has with inline engine is that the starting air valves will be only on one bank of cylinders. All the cylinders will not have air starting valves because the number of air starting valves that are on one side will be adequate to turn the engine to the required RPM where the momentum of the flywheel will capable of rotating and igniting the units of the other units, of the other ready to fire units. All right. So remember, air starting valves are only on one bank of cylinders. It does not make sense to have air starting valves on all the units. Only one bank, because one is capable of rotating the crankshaft and thereafter the firing can commence because the flywheel gets adequate information. The phone call, rubbish, sales. It's a blank. So it does not make sense to have air starting valves in all of them. The exhaust pipes are all kept in a very safe position, which will not cause any fire or injury to personnel. So they are kept in the middle over here. So the exhaust units deliver the air here, exhaust gases here, and these proceed actually to give the gases to the turbines. And above these exhaust pipes, there is what is called a catwalk. Catwalk is for the engineer to walk on and go along from one unit to another unit to make their inspections. On board the ship, you'll be required to open these covers and check whether the exhaust valve is continuously rotating or not. Because if it doesn't rotate, that valve is going to give problems. Okay. On the other side, you have the scavenge manifold. This scavenge manifold is to provide air to the cylinders. After the combustion takes place, the exhaust gas goes on to the other side into the exhaust pipes. The entire engine is based on what is called resilient mountings. The resilient mountings are like shock absorbers and they are mounted on the tank top. The tank tops are reinforced with vertical girders just below the reinforcement or the support for the engines. So these help in reducing transmission of vibration from the engine to the tank top. At the bottom of the engine, you have what is called the sump, where the oil is stored. And there's a drain cock, which has to be very carefully closed. And of course, when you're going to change the oil, that is the only time when you will require to drain the oil and change the oil. So this is your V-type engine. Remember the characteristics. If you are required to draw, you may have to draw this diagram. I've made it as simple as possible. If you want, I think most have seen what is a V-type engine. V-type V-I-E-S-E-L engine. V-I-N-E-S. V-type diesel engine. Let's have a look at it. It will give you a pictorial pictorial diagram. Here is your pictorial diagram of a V-type engine. Yeah. Okay, now here it is. Of course, looks a little complicated here. These are one crankshaft, both of them are joined. Here the angle is definitely a lot less than 45 degrees. It's about 30 degrees, it seems. Okay, so you have V-type compressors also. This is your V-type compressor. So V-type engine, yeah, this is the best one. Here's the best diagram. Oh, no. So this is the best one. Oh. I hope you can see this diagram. Here's a V-type. This is A bank and this is B bank. And then you have a flywheel. And of course, hydraulic dynamometer is there. Diesel engine is there. So this is what it looks like. Alternatively, you can have a look at this one. This is also a diagram with a V-type engine. So two pistons are connected to one. Let me just put it up on top. Where is this V-type engine? He says I already have it. Now I skip it. So this is your V-type engine. What you see, both are connected to one crank throw. Okay, let's move on. Next, what we have is bed plates and cylinder blocks are of heavy cast iron. This gives good vibration damping properties. Crankshaft is underslung. It's made of forged steel. Connecting rod is of the marine type and of two pieces. That means one will be the keep and one will be the main connecting rod part. Pistons are single piece or two piece. You see engines which are asking for much more of power, which have higher exhaust gas temperatures or combustion temperatures. You cannot afford to have aluminum alloy. So instead of aluminum alloy piston, you have a two-piece piston where the upper part is made of cast steel and the bottom one is made of thin cast iron. So the compromise is higher temperatures for a little more added weight. That's the basic requirement. Liners are made of grey cast iron, which are spheroidal cast iron, and are bore cooled. Use of residual fuel. Now, residual fuel using in medium speed engines has given rise to a lot of problems regarding ignition, knocking of engines, after burning, carbon deposits, all these things are there. So use of poor quality residual fuels, the problems and consequences are, number one problem is ignition difficulties. Sometimes they don't start. So to start, you have to make sure that the engine and the oil are both in readiness. Second big problem is increased wear of running surfaces, liner and piston rings in particular. See, catalytic fines are one of the most common factors which cause for wear and tear of engine. Apart from this is combustion debris and ash. Ash also plays a role in causing wear down of your cylinder, liner and piston ring. Ignition difficulties are mainly with ignition delays, knocking of engines after burning. Knocking of engine is caused on account of ignition delay. It is a rapid combustion of fuel within a short time because the fuel which comes into the cylinder does not ignite. And by that time, more and more fuel comes in. And when it does ignite, the entire fuel explodes or detonates. And that amounts to detoning. After burning of fuel means the combustion process is continued even after the combustion stroke is completed. That is what it means. The wear that arises on account of using residual fuel is abrasive wear, adhesion, which is cuffing, and corrosion. All right, these are the main wear. And what are the consequences? Poor starting, misfiring, knocking, damage to bearings. Whenever there is knocking, the force is ultimately transmitted to the bearings at the bottom. It is like a hammer blow on top of the piston. That is why it is knocking is a big damaging element. Ignition delay gives low peak pressure, after burning, carbon deposits, poor power development, wastage of fuel and poor economy. That is the bottom line. After all, money goes. rapid wear and possible damage of liners and rings and bearings. Catalytic fines in fuels accelerate wear. That is true. Catalytic fines are mainly silicon oxide and aluminum oxide, if you remember. Corrosion can be cold corrosion as well as hot corrosion. Both are increased because the residual fuel also contains some amount of sulfur. But of course, now with low sulfur fuels being utilized, the amount of cold corrosion has diminished. But hot corrosion can still be there because the quantity of vanadium is still not given much of reduction. And the amount of sodium that comes from seawater is variable. So if the proportion of sodium to vanadium is 1:3, then the catalytic effect of formation of salts is multiplied. And these salts, there are 8 in number. They're called vanadates. Sodium divanadate, trivanadate, all the vanadates are there. And they are the main cause for hot corrosion. All right. So I will send this link to you. So you will continuously read up on the information given in the PowerPoint. And if you have any questions, definitely refer to any part that you have difficulty in understanding. And we shall clarify all the points that are there. Now let me take a quick attendance. This is already 11:08, up to 11, 2 minutes I have. So 78, what number does it start from? This is section C.
Yes, sir.
78, okay. 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 89 missing. Section C. 8089, maybe withdrawn. 90, 91, 92 is not there. 93, 94. Kathuran Ashwin, 95?
I'm 95, sir.
Okay.
Yes, sir.
95, 96, 97, 98, 99, 100. Kundan Kumar Sharma, are you 8, 101 or 102?
So 102, sir.
102. So 101 is not there. Why is it echoing? Okay, because of his micron. Okay. 4, 5, 6, 7, 8. All right. 9, 10, 11, 12. Mrityunjay Kumar Rana, you're 8, 1, 1, 3 or 4?
1 4, sir.
1, 4. So 1, 3 is missing. 8, 1. Maybe he's withdrawn. 5, 6, 7. Okay, that's all. Up to 17, no? Neha? Yeah. 8117. Okay, that will be all for today. Yes.
Sir, actually, we as a section wanted to request you that our syllabus is lagging a bit compared to other sections. So, whenever you're free on weekdays, can we arrange for some extra classes?
Okay, very good. That's very good. But everybody should attend.
Sir,
now, if 20 boys attend,
attend.
and then those boys will keep, sir, you didn't take my class. That is the problem. Okay, I will give you a time, date, and it will not be during the class program because other classes also have to be attended to. It will probably be off the usual class period. Maybe at night.
Yes, sir,
okay.
we are good with that.
Okay, okay, that's good. Okay, that will be all. Let me stop the recording part of it. Stop recording. Okay, take care, all of you.